worth it. Okay. All right. So, Mr. Arrhenius from Sweden said that acids are substances that dissociate. Do we remember the word dissociate? What does it mean to dissociate? To split apart. They dissociate in water to yield. Do you guys know what yield means? To yield means to produce. Electrically charged ions, one of which is the hydrogen ion. So this is the key thing here, is that acids release hydrogen. Okay, hopefully you knew that already, but just to hammer that point home. Now we can write the dissociation equation. Okay, this right here is the dissociation equation. And basically what it is if you take some HCl, which is a gas, and you dissolve it in water, then what we get is, and I'm just going to pop over to the picture for a moment, because you can see we have these HCl gas molecules, but when we dissolve it in the water, the H plus ions and the Cl minus ions all float around independently. So the H and the Cl start out being together in the little molecule, but when we put them into water, the ions separate, they dissociate. And because they are dissolved in water, their state is now aqueous. Okay, so they go from being gas to when they're dissolved in water, they are aqueous. And you can see they are ions. We have the plus charge and the minus charge. We might have something more complicated where we have a polyatomic ion, all right, and the H plus ion is separate from the BrO3 minus ion. That again is dissociation. Now there was a question this morning asking me, what's the difference between dissociation and decomposition, right? Because these look a little similar, right? Well, let's go to, if you have some blank paper upon which you could write, that would be great. So go grab some paper if you need it. Yes. Yep. So we're going to compare decomposition versus dissociation. And let's just take a look at, let's say, for example, NaCl. If I have a solid, I could dissolve it in water Whoops, I put it on the wrong side. We're going to melt it, and we're going to apply an electric current. What we're going to end up with is sodium with a 0 charge solid. So that is elemental sodium, not part of a compound, plus, if I have elemental chlorine, excuse me, what should I write after the Cl if it's elemental chlorine? I should write a 2. And its charge is 0. Normally we wouldn't write the charges, but because we're looking at the difference between decomposition and dissociation, we're going to do that. Now, again, also normally we would not write these little charges here, but in the compound, sodium is positive and chloride is negative. So in this process, sodium went from being positive to being 0 charge. So sodium actually gained an electron. And chlorine went from being -1 to 0, so it actually lost an electron. Sodium chloride, what are some of its properties? Salt. NaCl is a whitish crystal, yes. It is yummy on your food. It tastes salty, yes. Now, how about sodium metal? See if we can get that up and running. Sodium metal is a metal like any other metal. It is solid, it is shiny. Yes, it will conduct electricity. Let's see if I have a picture of sodium. It's not going to come up. No, we're not going to try even for that because it'll take way too long. But does anyone know what happens if you put sodium metal in water? It explodes. So if you were to eat sodium metal instead of sodium chloride, your stomach would explode. Yes? So do you see how we are making things with vastly different properties? Okay, so sodium with a 0 charge, solid, explodes in water, and it's a shiny metal. Chlorine gas is a toxic gas. So what kind of a change did we have when we decomposed the sodium? We took sodium compound and we turned it into 2 separate elements. What type of change is that? Is that chemical or is it physical? That is chemical. We started with something you might sprinkle on your food, and we finished with 2 substances which you don't want to go anywhere near any orifice of your body. Okay? So this is decomposition is a chemical change. But dissociation, we're going to start again with NaCl solid. When it dissociates, it splits apart into ions, Na plus aqueous plus Cl minus aqueous. And remember, in the compound, the sodium was positive and the chloride was negative. This time all we did was we dissolved it in water. Now I know we don't normally take salt water and like sprinkle it on our food, but could you if you wanted to? And it would still be edible. Yes, it would be a little soggy. However, people do brine things. Have you heard about brining things? And in fact, you know, if you get something like cured ham, they'll have soaked it in brine, which is essentially salt water. Okay, that's how it gets that salty flavor. So the properties of the solid and the properties of the aqueous substance, they both taste salty. You can evaporate the water, and what will you get back? You'll get salt, yes? So this is the same substance, just in two different states. And this is a physical change. So if you're like, what's the difference? Decomposition is a chemical change, it's a chemical reaction, whereas dissociation is just a physical change, it's just a change of state. Okay, you still have the compound at the end, it's just dissociated. You are not going to have to explain that difference, but it might help you, you know, if you're like trying to predict the products of decomposition, it'll keep you from, you know, sticking charges on the ions, or if you're doing dissociation, it'll help you remember to put those charges on the ions, okay? Okay, and I can print out a copy of that for anyone who wants it just a little bit later. So let's go back to page 75. And remember, we had the acids, which produce H+. What do bases produce in solution? They don't produce H+, they produce OH-. Okay, so we have our bases, we get OH-. So we look at our, again, here we have our dissociation equation. If I take some NaOH solid and we dissolve it in water, it separates into Na plus ions and OH minus ions, which then float around separately from one another. Let's take a look at what that looks like in the diagram. There we go. You can see we have a lovely little NaOH crystal lattice. And then floating around in solution, we have Na plus ions, and we have OH minus ions, and those ions all float around separately. Now, let's just take a look at barium hydroxide, because there's one thing that's different about that, and that is that the hydroxide has a 2. Yes? That means when it dissociates, we would have a barium, 2+, and we would have a hydroxide, OH-, and we would have a hydroxide, OH-, 2 hydroxides for every 1 barium. And when it dissolves, you get 1 barium ion, and you get 2 separate OH ions. And when you have 2 separate OH ions, you're not going to say OH minus 2. What would you say instead? You would say 2OH. Okay, when you put the 2 on, when you put the 2 outside of brackets, it means they're attached. When you put the 2 at the front, it means they are separate. So whenever you have a subscript and you have a dissociation, that subscript becomes the coefficient. Yeah? It's fairly straightforward, not a big deal. Okay. Are we good to scroll? Bases are ionic compounds. They are specifically those that contain hydroxide ions. And finally, we're going to get to the last category, which is salts. And salts are any ions that dissociate in water, any compounds that dissociate in water to form ions, but neither of those ions will be H or OH. So basically any ionic compound that does not contain hydroxide. Okay, so salts are all ionic compounds that do not contain hydroxide. So if we had NaCl, we wrote this yesterday, that is our dissociation equation. You just split it up into its ions. Don't forget to write the charges, and when they are split up, they are aqueous. What if I gave you Li3PO4? And I wanted you to write the dissociation equation for Li3PO4. I would have to separate them. Who are the 2 ions? Lithium, Li, and PO4. Now, in order for this to be a proper dissociation equation, what do I need to include on that Li and on that PO4? I need to include the aqueous, and I also need to include the charge, yes. So Li is +1. You can look up phosphate on your pink sheet. It is 3-. And have I forgotten anything? Yes, because we have 3 lithiums, we need to produce 3 lithiums. Yes? Okay. I would like you guys to try these exercises. So you're going to classify the following as a base, which contains hydrogen, an acid which contains hydrogen, bases which contain hydroxide, and salts, which is basically anything else. Okay, you're going to classify them, and then for part 2, you are going to write dissociation equations. I will give you about 5 to 7 minutes to chug through those ones, and then we're going to do some neutralization reactions. Mm-hmm. There we go. Okay. Okay. Here's our Lewis structure for HBr, yes. And let's say that I decompose this. And in fact, you know what I'm going to do? I'm going to replace that line with a pair of dots, so you can see that one of those dots came from the hydrogen and one of them came from the bromine. That's hydrogen bromide gas. Yes? HBr. When you dissolve it into water, the H comes off and it leaves its electron behind. So it doesn't have that electron anymore. So it's now positively charged because it lost that electron. The bromine has that extra electron, yes? And so the bromine is negative. So those will actually be now separate from one another. This would be an H+, this would be a Br-, and they would float around separately in water. And do you see how both of their shells are filled and stable? Okay. But if we take HBr and we're now going to, so this is dissociation. If we now are going to do decomposition, we actually want to take the hydrogen and make hydrogen stable all on its own. And there's no way that this hydrogen can be stable without having this bromine around to have its extra electron, right? Like it needs somebody to give that electron to. So we're going to take bromine here, Br, la, 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 la. And we're going to take another one of these because we are going to need another one. Okay, these two hydrogens are going to say goodbye to the bromine, and they're going to share their electrons. Do you see how now both of them are satisfied? Okay, what's the charge of that hydrogen though? It's neutral. Yes, because nobody is taking any electrons from anybody. Now the bromines, they're going to get together with each other and they're going to share their single electrons. Okay, and so we'll end up with Br and the charge of that is also 0. So we now have H2, each with no charge, and we have bromine, Br, neutral atoms. So that's the difference between dissociation, where you have an H plus together with a Br minus, splitting apart into H plus and Br minus. So they're really the same ions. There's been no movement of electrons. The hydrogen didn't really have its electrons before. Now the bromine does have the electrons. Now we have a situation where everybody's neutral. Okay? So that is why when you dissociate, you don't write, if you have HBr, you're not going to have it become H2, because H2 is neutral hydrogen, and it's H2 because it needs to share those electrons with another H. What you have is you have H plus, which is already stable because it has emptied out its valence shell. If that makes sense, that's excellent. Otherwise, you can just remember that when you're dissociating things, they just dissociate into single ions, unless it's a polyatomic ion. Okay, and you don't put 2's with them or anything. You just put the charge on it. Okay? Now, we're actually going to move on. I'll give you some time to work on that a little bit more later, and we're going to go to 6.3H. Okay. And we're going to look at predicting the products of neutralization. So this is page 77. So we have sulfuric acid, and if we have an ic acid, what's the ion? Sulfate. And I know there's a F here, but it doesn't matter if it's an F or a pH. And we can look up the formula for sulfate, which is SO4 2 minus. If it is an acid, who is the other ion that it gets paired with? H. So we have H plus. So what is the formula for sulfuric acid? H2SO4, because we need 2 positive hydrogens to balance the 2 negative sulfates. So we have H2SO4. That's our reactant number 1. It was completely neutralized by aluminum hydroxide. Aluminum is 3+, hydroxide is -1. So what's the formula for aluminum hydroxide? AlOH3. I got 2 people complaining at me. I should have lots more people complaining at me. Why should you guys be complaining at me? Because it's wrong. Yes, why is it wrong, Timon? There's no brackets. Yeah, absolutely. We need to have the brackets there because we don't just have 2 hydrogens. We have 2 of the O and the H, both of them. Or not 2, sorry, 3. We have 3 of them. All right, we're going to predict our products. Now, do you remember that neutralization is just a special type of what? Double replacement. How did we predict the products of a double replacement reaction? First thing is we wrote the ions, yes? So we're going to write out all the ions. So we have hydrogen ion, and we have sulfate, SO4 2-. We have Al 3+, and OH-. Wrote ions, write the ions. What do we do once we've written the ions? We do the outside ions. Okay, so we're going to take the H and we're going to put it together with the OH, which gives us H2O, or I'm going to write it as HOH because it's going to make my balancing life a little bit easier. If you find it easy enough to balance writing it as H2O, that's also perfectly fine. Okay, your choice. What do we do after we do the outside ions? We do the inside ions. Okay, and do we go forwards or backwards? We go backwards. So it's going to be aluminum, Al3+, SO4 2-, gives us Al2, SO4 3. Now, to make your balancing life easy, you should start by balancing the ions in which compound? The most complicated compound. Okay, so this one right here, it's got all kinds of subscripts. So this has the most subscripts. So it is the most complicated. That means we're going to balance the aluminum and the sulfate first. We have 2 aluminum. So we're going to put a 2 in front of the AlOH3 on the other side. We have 3 sulfate. So we're going to put a 3 in front of the H2SO4 on the other side to give us 3 sulfate there. And then we're going to look at either the hydrogen or the hydroxide. Doesn't matter which one you do. 3 times 2 is 6. And if you do it that way where you balance the most complicated thing first, that 6 is going to fix everything else, because if you look now, the 2 also multiplies by 3 to give you 6 hydroxide. Is good? Okay. Do we want to do another example? Okay, let's do carbonic acid. And in fact, let's do it the other way around this time. I'm going to write my base first this time. So we've got sodium hydroxide, which is NaOH. And that's going to react together with carbonic acid, which is based on the carbonate ion, because we've got Ic8. And so carbonate is CO3 2-. How many H's do we need to go with our CO3 2-? We need 2, so it's going to be H2CO3. Now we write our ions because we're predicting the products just like we did for double replacement. We have Na, which is +1, OH, -1, H plus, +1, CO3. You can look that up on the pink sheet. It is 2-. We've written the ions. Now we're going to combine the outside ions. So that's going to Na plus CO3 2-, so we need 2 NAs to give us 2 positive to balance the CO3. And we now have H going with OH. So that gives us H2O, or as I like to do it to make balancing easier, HOH. But like I said, if you prefer writing H2O and don't have a problem balancing, go for it. All right. Who is the most complicated thing here? Probably the Na2CO3. Usually you're going to look for the salt and you're going to balance the ions in the salt. Okay, and then everything else will just sort itself out. So we need 2 NAs because we have 2 here. So let's put a 2 in front. We only have 1 carbonate. And oh look, 1 carbonate. So let's look at our hydroxide. We have 2 hydroxide. Let's put a 2 there. And isn't that lucky for us? We also have 2 hydrogen, and we have 2 hydrogen, and everything is good and done. Yes? If you were asked to look at the states of this reaction, this will be optional. The only reactions where you need to write the states will be double replacement. Okay? So if you want to be enriched, you can try writing states for everything. Okay? But if you're like, nope, only double replacement is required to write the states. We good? Okay. What's water? What state is water? Liquid. We all knew that, right? We know water's a liquid. And just like in a double replacement reaction, our reactants have to be aqueous so that the ions can move around and recombine. And then you can, if you want to, check on your blue sheet to see if sodium carbonate is aqueous or if it becomes a solid, but that's optional. I happen to know that sodium is an alkali, so it's always soluble, so I happen to know that that one is aqueous. But like I said, if you don't want to put the states in, don't worry about it. Okay? I hate to do this, but we're going to do one more thing, one extra thing, because I broke it in half in my other class, and I feel like I never got them back after we went and did some work. So we're going to do organic acids. C something, H something, COOH. Becomes C something, H something, COO, and then we have the H. So when this dissociates, it is this hydrogen that comes off as H+. That's weird, right? Because the cation is on the wrong side. Normally the cation is at the beginning, but here the cation is at the end. talking about this at lunch. Like, why are they sprinting and screaming? A lot of sprinting and screaming going on these days. Oh my God. Okay. So, C something H something COO, and it's always going to be -1 because you've always just got one hydrogen. Yes? So we can then take a look at an acid reaction. We can have, let's say, for example, CH3 COOH plus NaOH. I appreciate you stopping them. No, it's good. I was like, this is stopping people again. That was good. Yeah, no, I appreciate it. I told them we were talking at lunch about screaming, running, pumping students. And well, but they were pumping. They were sprinting. I don't know. Probably. Last time. Okay. And it's so funny because Mr. H is like so mild-mannered most of the time, but we learned, he's like, no, you have to come to a basketball game because he coaches basketball, and apparently he's gotten like in trouble from the refs and stuff at the game because like he'll yell and stuff. Anyway, got a good set of lungs on him. All right, so we have our ions. Once again, we're going to split it into ions, and this time, remember who's going to come off as the positive ion? The H. Okay, so it's going to be that H, and the other ion is going to be the CH3COO minus. I didn't write that very well. They should be in line with each other. That's irritating. There we go. That's better. And then the NaOH is just like normal. So we'll have Na plus and we'll have OH minus. And do you see what would happen if we tried to do outside ions and inside ions here? We would end up with two negatives together and two positives together. So you just have to be, certain of yourself and go, I know that two positive ions do not go together. I know that I need to take my negative ion here and put it together with the positive ion there. Yes? And I need to know that my positive ion goes first and my negative ion goes second. So I'm going to take those two and put them together. So my product will then be NaCH3COO. And then my other two ions, well, that just makes water, or HOH. And that's good, right? Do we want one more example, or are we good? One more? No? You're good? Excellent. So you're going to work on page 78. And then 91 to 92, odd letters only, ACE. And then 64, odd numbers only. This is a little review of single replacement, but it requires you to use your activity table to see if there is a reaction or not. So you'll need your blue sheet. And if you're interested in doing enriched stuff, that's the naming of organic acids. Yes, you certainly can.